Ah, yeah. Olá, Porto. Eu sou Matheus e é sempre muito bom estar aqui. And that's all the Portuguese I got for now, but happy to discuss more after. Yeah, and we're here to discuss a lot about React, some of its internals, and advanced performance patterns for React and the web as a whole. So a little bit about me. This is me. I am a staff software engineer at this company called Medallia. It's a CX company. I'm part of the React Summit New York committee, and I'm a GD in web technologies, and you can find me everywhere as Y Combinator, including all social media. Just so that I get to know a little bit about you, so who here works with frontend? Uh, okay, vast majority, and with React? All right, that makes a lot of sense. So before we start, I'd like to share a general preamble on my motivation for coming up with this workshop, and specifically with its table of contents, and then we'll get to dive a little bit more deeper into the topics we have for today. So my key motivation here is our customers and our businesses. And this is a screenshot from a few years ago when I was checking our real user monitoring of the app I maintain. I was checking all the list of browsers that had visited that app in the last month. And the first ones were a bit obvious, so definitely iOS and macOS with Safari. There was Chrome, there was Edge, and then mobile versions of these browsers. But as I went down and down, I started seeing something like Internet Explorer and Opera. But that's not the funniest thing. The funniest thing is when I saw Blackberries or Samsung browsers or even a PlayStation console, which is super funny because my product are surveys. So that even made me wonder who was opening surveys on a PlayStation console. So we live in this reality where, depending, of course, on what solution you're building, you have to ship things for a wide variety of browsers. But not only that, a wide variety of connection types. And there's a few parts of the globe, including certain parts of Latin America and Sub-Saharan Africa or Southeast Asia, where there's also a wide bandwidth mix, and things that for a lot of us are standards like 4G and 5G are not the standards that there are in some regions. Not to mention that sometimes even when we're talking about the same technology, this is a charge for LTE, the same technology can mean a lot of different things depending on where you are. So in certain parts of the globe, LTE can be 6 megabits per second, but it can go all the way to 44. So even the same thing. Not to mention that there's a bunch of interesting research showing the implications of slower experiences to users. This is one of my favorite ones, and it's super old. It's from 2009. And apparently 40% of British people at the time, they had become physically violent towards their computers at least once in their lives. And then this pattern repeats over the years, like this one by Hardware, which is a very famous consultancy. They said that a 500 milliseconds delay and resulted in up to a 26% increase in frustration and up to 8% decrease in engagement. And throughout the years, Ericsson also found out that, this is also super funny, that delayed web pages caused a 38% rise in mobile users' heart rates, which was comparable to the anxiety you get by watching a horror movie alone. And then there's also plenty of research connecting that to the business impacts of such experiences. This is one by Akamai and Chrome, so both of them are always conducting interesting research around web performance and stuff. And they were investigating different platforms in the States, mostly e-commerces, and they observed how the conversion rate dropped as the TTI, or time to interactive, of the page increased in the observed web applications. All leading up to research showing how, for example, 53% of users would abandon a website that took 3 seconds to load. For me, all of that is already super mind-blowing. And if you're interested, you can check more about this kind of things. Alex Russell, he publishes yearly this thing called The Performance Inequality Gap, where he addresses a lot of these things. The second half of the intro also has to do with the industry we live in and we work at. And this is probably one of, and now we get to talk a little bit more about React. So this is one of the probably one of the most famous talks in the world of React. It was by Pete Hunt at Conf Europe 10 years ago, or actually more than 10 years ago. And he said, with React, you can build applications without even thinking about performance, and the default state is fast. And I do think that at the time this was true. This was, again, a talk called Rethinking Best Practices in 2013. But I also think that it's tricky to call something fast when it's even trickier to define what's fast. Because when we're talking about a fast experience on the web or even on a mobile app and a mobile page, we can be talking about the perceived load speed or the load responsiveness or a bunch of other things, all the way up to how smooth that is, like the transitions and animations of that page. And what I think that would happen is throughout the years, besides a bunch of open source projects, is that React started embedding in itself a bunch of perf mitigators so that the default state continued to be fast. So at the time of class components, we got should component update, and we also got the ability to extend React.pure component. And then for functions, we finally got React.memo. And then we entered the hooks era, and we started with memoization hooks like use memo and use callback, and we went all the way through more and more hooks like use transition, use defer value. We got suspense and a bunch of other things, and then the surface area of the thing just started getting bigger and bigger. And I don't know about you, but whenever I'm thinking about all of these things, I also think a lot about this post. It's called Silent Engineers. It's not about React itself, but it is about the hype and the even frustration in a community where this thing's always popping up. So in the post, there's a quote where the guy says, "Why browsing Hacker News, I sometimes get a feeling that every developer there is working for Fang. Is there's always posts from those people doing some hype stuff. Or you might think that PHP is never used nowadays because whenever it's mentioned, everyone is hating on it in the comments." And he goes on, "But let's be straight, that's like 1% of all of the developers out there. The rest of us are just lurking and coding with the language of their choice and being happy about it, be it Fortran, COBOL, Perl, PHP, and so on." So this is the foundation for today. I'm not here to talk about modern rendering practices or different approaches to hydration or things like islands. For example, we had a very good talk about islands in Astro earlier today. I do have a talk about that, by the way, that I was presenting here in Porto a few years ago. However, I'm here to talk about some challenges that I faced when trying to make things fast here and there in some apps I've worked here. And so this is a really good analogy where it's famous. Some of you are already laughing because you've probably seen this before. So it is about the fact that sometimes making things fast on the web is like drawing a horse. You just start with those 4 very simple steps, and then you add some tiny details, and you're good with it. So I'm here to talk about some of these tiny details. By the way, this was supposed to be one of the fun parts of the talk. So for that, this is how I want to approach all of these topics. These are the things that influence me. The first one is this post called Application Holotypes. It's by Jason Miller, the creator of React. He is a genius of web performance, and in 2019, he basically drafted this post where it was all about, he basically laid some kind of possible web applications you might want to build, like a social network, a game, an e-commerce, and all of that. And he went there and discussed it. Okay, here's how you should approach every single step for this specific kind of thing. So I want to talk about things that may work in very specific scenarios, especially because a few years after Ryan Corniato, the creator of Solid and an ex-core committer of Marco, he then expanded on that post of application holotypes, where for each of those different archetypes of applications, he would approach, okay, here's how I think you should handle interactivity, here's how I think you should handle rendering and hydration, and etc. So that's what I want to do. I want to revisit a couple of CS concepts with you today, and so that we can understand how some of these tools, and by these tools I mean mostly React, work under the hood, and mostly why they work the way they do. So we'll see a little bit of the source code of React. That's why it says internals in the title. But at the same time, I do want to bring some real world case studies from small, medium, and even bigger companies I worked at. And at the end of the day, we'll have seen and co-reviewed some micro experiments and their results. So there will be no larger project that you will be building throughout the next 2.5 hours. So it will be a lot about micro experiments and co-review. So if I were to summarize all of that I've been saying for the last 10 minutes in a mantra, that would be, I want to, in a way, empower you with knowledge and tools to help you tackle different React and overall front-end performance challenges, be it personal or professional projects. And I want to try to bridge the gap between some CS concepts and practical front-end development. Last but not least, I'm a lot inspired by the workshops and classes in front-end masters, and also by the talks that used to happen at the Velocity conference. So Velocity used to be a conference that happened in New York, San Francisco, and Europe too. And they had a lot of very, very interesting performance talks. All of them were 90-minute talks. So a lot of days will feel like a longer performance talk. Last but not least, the topics, we'll talk a lot about scheduling, scheduling strategies from programming languages and scheduling concepts from computer science. We'll talk about how scheduling works a bit in the browsers and in React. Then we'll discuss a variety of other techniques, including browser techniques and things that work outside of React too, like windowing, all the way to some algorithms too. And last but not least, we should also talk about measuring. If we want to talk about performance and how to optimize it, we definitely also want to talk about how to measure what we had before and what we had after. So the methodology is, there's a GitHub repo, which I'll share the link with you, and you can clone that. If you don't want, you don't have to, because I'm going to be sharing my screen. And again, it's not like there's a specific exercise for you. It's more like if you want to have the code hands-on for you to experiment with as I experiment with. I will also be sharing all the slides you see with you, so if you miss anything or if a certain concept is not clear, you have access to all of that. I'll have some question slots at the end of all the complex sessions so that we can tackle things as we talk about it. And last but not least, there's going to be a 10-minute break that I plan to sync with the official coffee break with the conference, but before running the break, I'm going to ask you, hey, do you feel like going on a break? So, this is the link to the repo. This is a QR code, which can be inconvenient for if you want to git clone it. If you want to just have the code on your repo so that you can bookmark it in your phone, you can follow this QR code. But you can also, this is the GitHub URL for it. So I don't know if for you at the bottom, yeah, for people at the back, it might be, the font size may not be very big, but I'm going to leave it for the next minute on the screen. And again, you don't have to clone it if you don't want to, because I'm going to be screen sharing the whole time. So it's github.com/ycombinator and then /workshop-react-internal. So it's basically a workshop and then dash the whole name of the workshop. It's naked. By the way, do you prefer the URL like this or in the QR codes like this? QR code, all right. So I'm going to leave the QR code on the screen for a few more minutes and then the repo, by the way, is a pretty standard Vite app with some basic client-side routing, just so that we can demo some of the concepts. You can yarn install and yarn dev it, and it should be good to go locally. So I still see some people taking pictures. I'm gonna wait a little bit more. All right, I think we can move. So yeah, as I mentioned, It's a pretty standard React app, hello world kind of app. Yarn install it, yarn dev it. Another thing we'll be using that if you want you can install, but probably some of you even already have it. We'll use React developer tools here and there, especially the profiler. So keep in mind if you want to add it to the browser. And last but not least, for some of the topics, we'll be conducting some deep dives. But if a certain topic sounds super dense or complex, don't worry. Again, you have a lot of homework. Plus, I'm going to be around so we can talk more and clarify anything that's not clear. Finally, the first topic. So scheduling. By the way, I added those tiny flares over there. Is a way to signal that complexity of a certain topic. So for scheduling, we'll talk about fibers, about coroutines, about effect handlers, and then we'll talk about tasks and what it means to be a task on the browser. Also, what is a long task, what causes it, and some strategies for optimizing running those tasks. And then we'll dive deeper into scheduling in React, precisely how React organizes things under the hood, what kind of algorithms and heuristics it has, and a bunch of internal concepts of it. And then we'll take a few steps back and see how we can have any practical implications of those things. And last but not least, we'll talk a little bit about scheduling on the web and some upcoming things that are very, very interesting on React. So starting with fibers. I think that a very, very good introduction to fibers is actually if we inspect what a JavaScript function looks like, especially the anatomy of its stack frame. So if we could grab a very, very simple piece of code, a function that takes two parameters, creates a variable in there, adds them, and returns the result, and then a function call, pretty straightforward. If we were to model a simplified version of the stack frame for that function call, we would have something like the function itself, the parameters it takes, and some local variables. In this case, local variables is the result 4, and that's pretty much it. So we can draw a parallel between that and what React does internally. So if we were to model a fiber in React, instead of a function, we would have our component, which can be, for example, an avatar component that renders a profile picture. And then instead of the regular parameters, we would have props. Instead of local variables, we would have some internal state that doesn't really matter how you edit it, if it's a class or via hook. And that's precisely what fibers are. So there's this whole umbrella of the fiber architecture, which is this React-specific thing implementation of something that looks like a call stack, but for components and internal operations of React. And this thing gives React full control of scheduling what should be done. And then precisely a fiber as something analogous to a stack frame for that specific component, for that specific unit. Now that we are thinking in terms of units of work, we can take a few steps back and think about what happens with our components and when they turn into elements. So basically, we got our JSX or TSS templates. They go through the compiler, and we end up with a bunch of React elements. And after that, we have the reconciliation, which some of you may have heard about. And then this data from all of those elements, they are returned from the render method, is merged into this tree of fiber nodes. And we'll get to visualize what this tree structure looks like. And then here's the trick. Depending on which kind of things we're talking about, it can be a div, a paragraph, or something, but it can be one of the React internals abstractions like a suspense boundary or an error boundary, and etc. React needs to perform different kinds of activities depending on what it's handling. So each of those elements is converted into a node that is going to describe to React what kind of work it needs to do for that specific thing. If you want to check about it, you will see this mostly in the source of reconciler. I don't expect you to be able to read the font size of it, but there's this file within the React reconciler that's called React internal types, and you can really use to see this. You can go through this file that's in the source of React, and you can inspect the anatomy of a fiber, and they even have the flow type annotations. But overall, we were talking about specifying to React the different kinds of work it needs to perform. Another file that also exists within the reconciler, it's called React work tags. And in this file, you can see there's like dozens of lines React assigns a unique identifier for each kind of React abstraction, like a function component, a class component, the different boundaries, portals, and so on. So actually this list is an ever-living list, because as they add more abstractions, like the context API with providers and consumers, they will also be specified over there. And this very fact that React can so well describe these things makes via the fiber architecture, makes this a very convenient way to track, schedule, pause, and abort work on the browser. So the first exercise we can do about that is I have the application here running in localhost from that repo. And let me pull the code for that. So under fibers, I have this. Is the font size okay for people even at the back? All right. So here I am using this tool called It's Fine. It's a tool by the collective open source group called Poimandres. And it's one of those abstractions that allows you to interface with React internals and inspect them and etc. Poimandres are also the same guys behind a lot of famous state management libraries like Vaultio or Zustan, or yeah, you probably heard some of these names. So this is something very simple. All I'm doing is I'm calling this use fiber hook and assigning to something, and I'm constantly logging this fiber in the component that is running, and then I need to use this fiber provider to drop the component. So let me refresh this, and here in developer tools, when I console log my fiber, you'll see that there's just, yeah, let me zoom out a little bit. But you can see that these are all the information that React stores about that thing. And that includes the ref information. I said it's a fiber tree, so information about siblings and children, and also about props. So if I go all the way down here, remember how I mentioned that there are tags specifying different identifiers and things. And then if I go all the way down to this fiber node here, I can see my my H3. So this is this title. So this is the H3, and I can see all the metadata about its children. Here the children is just text. And you can see that I'm using, for example, Tailwind to style it. So class name is going to be this Tailwind thing. So overall, of course, we don't have to go through this entire tree and understand all of the metadata for the sake of this workshop. But this is how rich the fiber tree structure is underneath our React applications. And another thing we can do also is to try to implement them on our own. So I have a analogous exercise here that is called custom. And then in custom, I have a hook called custom_useFiber, and I'm passing this a ref. My ref is positioned precisely at my p tag here. And the source of this custom use fiber is it basically gets the element ref, it finds its value, and then it calls a function get fiber from the DOM, passing the current value of that ref, and get fiber from DOM basically inspects the keys of that thing and uses this internal React identifier. It tries to look for the first one. If it doesn't, it looks for the second one. It's called __ React fiber $. And then it returns the information as this fiber type. And then I have a second function that is highlight fiber. And what this highlight fiber does is it basically creates a DOM div with some styling so that, let's say I'm inspecting this, I can use that to highlight that fiber. So you can see under here custom, if I refresh, first of all, I'm going to have the same console log similar to the one we did using the library. And you can see also that there is a very fast here. Every time I refresh, the thing we created, that is the highlight fiber node. And then one thing we can do is move this ref around so that it's highlighting other stuff. So right now it's over my p tag. I can position that ref in my title, for example, and you can see now it is going to highlight that thing. If you've profiled React applications,
it actually does something similar when it's, let me open the React profiler. If I go all the way over here and I click highlights updates when components render, you can see that, let me refresh this. So this was, do you see how it draws lines, everything? So most of those developer tools, they are all using, and the same thing for React Native, by the way, they're all using internal React metadata to fetch this kind of information. And I know that most of us are not writing developer tools, but we'll see some actual interesting implications of that. And the first of them is actually manipulating those units of work now that we can understand them as units of work. So there's this concept in programming called homoiconicity, which is almost like a tongue twister. It's easier to pronounce in Portuguese, but this is basically a property of some programming languages in which the code used to express the program is written using the data structures of that language. So this concept is very common in common Lisp languages and in Clojure. And this is actually one example of a hello world in such language. So what we're doing here is we're binding x to the value of 1, and then we're incrementing x so that it returns 2 in the second line. And yes, if you're not used to it, people would find weird the amount of parentheses that these languages have. But what's interesting about this code is we can abstract this as a list with 3 elements, where the first element is a symbol, and we call it let. The second one is a vector with 2 elements, and then we have a second list with 2 elements. And the first vector is we have a symbol x and an integer, and in the second one we have the symbol that is increment, and then another symbol x. So this is, we're kind of like thinking about the abstract syntax tree of the language itself, right, at this point, and how it's abstract in terms of the data structures of the very own language. What's the connection with React? The point is, we just saw how all of those React elements that we code in JSX or TSX end up being just metadata. And just like in Lisp or Clojure, those components, they can manipulate their children and return completely different things based on that metadata. So one thing, this one is not an experiment precisely, but it's bringing pattern matching to React on top of that. So if you're, who here has ever heard or used pattern matching in any programming language? Right, yeah. So pattern matching is basically about specifying patterns in which some data should conform and then checking to see if it does, and construct this data according to those patterns. Again, another example in some other language, this one is in Haskell, and this is a very simple factorial function in Haskell where first we have the type annotation of that function, and then we have 2 patterns being matched here. First one is the base case where if we have 0, we return 1, and then the second one is the recursive call where when we match n and then return the factorial call of that. And then we can come up with more complex examples like the Fibonacci, where you have, again, first the type annotation, and then we have 2 patterns. For 0, we return 1. For 1, we return 1. And then we match n and return the computation where n is bigger or equal than 2. And then we return the recursive call of Fibonacci. What I wanted to show you at the end is actually this piece of React code, where basically I'm simulating some data fetching. So my data can be either text or some image. If it's text, it has a content. If it's an image, it has some source. And then I got a response from my API that can either be okay and contain some data, and then or it can be an error because it failed. And then I'm calling this hook that it's called use pattern match. And this hook takes a generic type and gives me 3 different components: match, with, and otherwise. So match is the wrapper, and it takes the response. And you can see that in the 3 with assertions that I'm doing, I am basically deconstructing as props, as typed props, by the way, because my hook gave me all of the types I need. And then I'm rendering, so at the end you will only see the children that actually matches your API response. And the way this is done is there's a lot of source code, but the part I want to focus with you is that there's this function called is when, and you can see that it takes generic types and stuff, but basically under is when I'm actually accessing metadata to see, for example, if the children of that match assertion is of type when, or if it's an otherwise assertion or something else. And another thing that I'm using is I'm iterating through the children by using the two-array utility of React children. And there are more other parts of source of that library that also is assessing component and element metadata to basically conditionally render different things in a very declarative, React-y way with all type assertions and etc. And this kind of thing is really powerful because you can mix and match that with first suspense and lazy, and also with some other APIs. So in this example, what we have is we have a suspense umbrella, and then I have an ambient light component, and then I have in my way a predicate props where I basically pass a function that tells whether the browser supports or not that specific API. The API is ambient light, and then it renders the children depending on that or not. It renders different children. So here we have pattern matching with suspense and React Lazy, having our users download only the component model that's actually matching the assertion. And this is an oversimplified example, of course, because I have only two cases, but you can write something that's very, very declarative with that. And with the pattern matching part, what we're doing is we're just manipulating elements as data. If you want to check, this is definitely not production ready. This is actually a small experiment I did in my previous job, and we did use that in production, but I don't recommend you to use, but it's still a fine, an interesting exploration of the source. So the message here, the key takeaway is how using fibers React can pause, resume, and restart any work to rendering things as new updates come in, and we'll see which heuristic it uses, by the way. It can also reuse work that was completed previously, and it can split units of work and prioritize them based on their importance, and we'll also talk about how it defines importance. This is the It's Fine library, if you want to check. And it's actually used in production by a lot of apps and libraries, including React Native Skia. So React Native Skia is some very famous library in the React Native world. And there is another more recent library that has that is quite similar to It's Fine. It's called BP. And BP is created by Aiden Bay, the guy behind Medium.js, which is a faster alternative to JS. And the thing is that BP is used under the hood by a tool called React Scan, which is an inspector that allows you to see when it's like an extension to the React profiler. It's not a Chrome extension though, but it's like an extension to the profiler that gives you more highlights on how your components re-render. Another interesting thing is that fibers, even though there is a whole fiber re-architecture of React that happened back in 2016, fibers are not a React concept. For example, fibers are also a thing in Node.js. And this brings a very, very interesting conversation about asynchronicity in JavaScript. Because this is what async in JavaScript is what some people consider to be contagious. For the simple fact that you've probably been in this place where you refactor some code to use async await, and then you have to refactor the code calling that, so that's also an async function awaiting for that. And then you go all the way up, and then all the way up, and so on, until your entire code is async. Some people in computer science, they describe this by function caller. There's this interesting post from 10 years ago called What Function is Your Caller, where the author explores that mostly in JavaScript. Here's a guy from the Go community. And the other point about that is that asynchronicity isn't free either, because on every async function call, what's happening underneath is that the engine has to allocate those callbacks and store them, and it has to also take another trip to the event loop before invoking those callbacks. And there is a very, very interesting case study of that, and it has to do with Sass, the CSS preprocessor. Who here has ever used Sass, by the way? Yeah, it's fairly popular. So the Sass compiler, I'm not sure if it's still like that, but it used to have two main functions for compiling Sass code, one that was sync and one that was async. And the async, of course, got super popular in that boom of async await and promises in JavaScript, because it enabled async plugins like Webpack SaaS Loader and similar stuff. This was for Node SaaS not a problem, because Node SaaS was built on top of C++, and they addressed a bunch of performance problems at C++ level. However, another very, very popular implementation of SaaS called Dark SaaS, because it was running as pure JavaScript code, it was subject to JavaScript asynchronicity details of implementation. So what happened as an outcome at the time is that the async version was actually far slower than the sync one. And then they started using this package called Node Fibers, which was built on top of the concepts of fibers and coroutines, to implement the async API using the fast sync code. This is the Node Fibers repo. However, there is something very interesting that happened 4 years ago in Node SaaS, that was basically V8 changed how it worked internally, and then Node.js changed it to reflect that. So from Node 16 onwards, Node SaaS stopped working, so this was a breaking change for them. And this was even a big thing for SaaS. They wrote about it at the time and how was migration, and some of you may have even faced issues when going from one version, from Node 12 or 13 to 16, and having issues with your SaaS compiler. Another implementation of fibers that's quite a hot topic these days is Effect.ts, and one of the main abstractions behind Effect.ts is actually fibers. And outside of the React and Node realm, this abstraction is also super popular, because at the end of the day, you're talking about something that is a lightweight, cooperative, concurrent execution unit. So they're also super common in operating systems and also languages too. And a lot of things that they have a scheduler underneath them, they actually resort to fibers to schedule the execution of tasks. So some languages that have it built in these days, Crystal, which is fairly newer language, but Ruby already got fibers, and PHP also already got fibers. And even Windows, like the Windows 32 development library, they have had fibers for quite a while now, and the Carbonite SDK from NVIDIA also have them. And if you're wondering how old those are in Windows, for example, they've been available since Windows XP for desktops and Windows Server 2003. Not to mention that there are very interesting case studies like this one. This is from a guy from Naughty Dog. He was an architect, and this talk is from 10 years ago, and it was a case study on how they optimized the performance of Last of Us for the PlayStation 4 to run at 60 FPS using fibers. So it's a very, very interesting concept, which, by the way, reminds me of this talk at Chrome Dev Summit that the guy said, whatever smart thing you think you did, game developers did it 10 years ago. And I found it to be true for a lot of things in front end and React. And overall, the same author of the talk, he also mentioned that this attitude does not only work in the context of game industry, any other industry with strong architectural requirements can be a source of inspiration and knowledge for us to write better code for the web. This, by the way, is one of the main takeaways you may have from the entire 3 hours. It's like how we can learn in the web and in React, and how the team also learned by watching other stuff. Before we move forward, do we have any questions? Or if you want, you can also leave the questions for the end, or for over beers or coffee, whatever. All right. So the next topic are coroutines, and what prompted me was into going through coroutines was this post by Andrew Clark. He is one of the founders of the concurrent React umbrella of features, and he wrote that React tricked you into learning about immutability, Redux tricked you into learning about high-order functions, and Suspense would trick you into learning about coroutines. And you can see coroutines as a concept showing up in the history of React for some time now. The first thing was this PR by Sebastian Morkburg. He is the also core committer, and he is the founder of the Fibers architecture, and he laid the foundation of a lot of what's React these days. But they appeared before the fiber architecture happened in 16. They were experimenting with fibers as a specific component type. So this is actually a screenshot of the same file we saw 20 minutes ago, where there were identifiers for every single type of operation that React can perform. So this PR was introducing two new components, a coroutine component and a yield component. And the idea behind coroutines at the time, as opposed to what fibers gave us, was to give components explicit control over yielding and resumption of tasks. And by the way, we'll talk a lot about yielding and resumption of tasks. Not to mention that Node Fibers, the package we talked just now, they also mention coroutines. They actually say that coroutines are the same as fibers, which apparently is also a hot topic in computer science and operating systems people. And finally, another project by Meta also say that fibers are comparable to coroutines. When I was digging about that, I found different papers addressing the matter. There's one that is called Distinguishing Coroutines and Fibers. And one explanation I found is that it says when a coroutine yields, it passes control directly to its caller, and then it talks about a more specific type of coroutines. And then it says when a fiber blocks or yields, it implicitly passes control to the fiber scheduler. And it says coroutines are no scheduler because they need no scheduler. So if we were to digest that, I would say that with fibers, you have the control passed to a scheduler, which determines what to run next. In this case of React, is the scheduler of React that is also part of the open source React umbrella. As opposed to coroutines, you have the control passed to a caller, the caller, and handled by the code of the app. Elaborating a bit more, at the end of the day, you have both deciding when to drop control or yielding execution, which is something we'll talk a lot about in scheduling. However, in coroutines, they can actually be implemented as a fibers abstraction, where you have a fiber that always yields to a coroutine scheduler, to a scheduler coroutine. And fibers can be used to implement coroutines if you have each fiber communicating to that scheduler which fiber should be run when it yields. This is very, very CS specific. But you probably remember coroutines if you've used something like Bluebird. Bluebird was actually quite a thing before we had promises in JavaScript. And if you've never used Bluebird, there's also Co. Co is a library by TJ Holloway-Chuck, the guy who created Express, Jade, Stylus, and other 500 different packages. And those are all generator-based coroutines abstractions at the time. Not to mention that Lua is another language that has the concept of coroutines built in, and C++ from 20 onwards apparently also has them. And you can even find use cases, case studies, for example, of RethinkDB refactoring their C++ code base with coroutines. And Unit also has guides of optimizing performance with coroutines. There was a question slide here, but I don't. Oh. Sorry? Oh, interesting. Yeah, I've been. Nice. Thanks. Yeah, I only got languages no one could relate it to. So, thanks. Yeah, I've been away from Python for some time. Yeah, cool, thanks. Didn't know that. So, another concept that has also influenced React for a lot more than one could think is effect handlers. So, effect handlers, and this is probably the most complex one to give a proper explanation in a limited slot of time, but I'll try. It's basically an approach for you to think about computational side effects in pure contexts. In this approach, you have mainly two things: a effect, that is a set of operations, and effect handler, that is the thing, as the name suggests, that handles the semantic of how that effect is implemented. Bringing another example for another languages, so we've had Clojure, we've had Haskell, now we have F. F is a language, one of the very few languages that brings the concept of effects outside of the box. And this is a little hello world in F. So the overall syntax of the language can sound a bit weird for most of us, but in the beginning you have basic A-type annotation where we're saying we got a string for our name and an int for our age. And here we are defining the effect using this effect keyword, and we specify a type signature. And then here we got our effect handler, which, by the way, it will remind you a lot of the pattern matching example, where basically we have this keyword handler, and remember about that because I'm pretty sure I'll manage to connect that to React in a bit. But this handler has 3 branches down it, and all of them return something. So the first case is the most simple one, when we have actual no effect. We reach the end of the block, and we are returning Y. And those are the matches for our 2 effects, our getter and our setter for that. And here we have a 4th concept that is called a continuation, but for this one I will not manage to address it during this workshop. But think of a continuation as the rest of the computation that happens after you perform an effect. So how does that all relate to React? It does, to the point that actually Dan Abramov a couple of years ago wrote a post called Effects for the Rest of Us. So if you don't know Dan, he is the creator of Redux, and he was in the core team of React for many, many years. And in this post, he would draw an example of what JavaScript would look like if it had algebraic effect handlers. And the key parts of this code are here. So we have name, perform, and you're performing an effect, and then you have a handle block, and you resume with a certain value. So the first part, you can think of it as if you had a throw, try, catch pattern, but instead of throw, we have a different reserved keyword, in this case perform. Instead of catching an effect, we are handling it. And then this resume with would be something analogous to the continuation we talked about, where basically we're jumping back to where we first executed the effect. And you can see that there's no need for async await or anything like that. And that's another interesting thing about about effect handlers as a concept, because it doesn't really matter how we hold state as opposed to promise, because if we were to change in the future in promises, as we talked, like what color is your function, yada yada, you have to go with changes across everything. With algebraic effect handlers, you can simply stop the current process altogether until the effects are finished, and then you can pick up where you left off. Why is this relevant to React? So throughout the history of React, this concept influenced the team multiple times. Many years ago, they were experimenting with using effect handler structures to control for managing layout. So this is part of a repo that is under the official React.js org. It's called React Feature. People don't use this repo anymore, but it was basically a bucket for a bunch of ideas from the core team. You can check it, and you, of course, have the slides. This example was drafted by almost 10 years ago by Sebastian Mockburg. And then you have the second one, when they were redrawing the context APIs. So back in React 16.6, when we got the new context API with consumers and stuff, there was and did replace the legacy APIs. They were also experimenting with it, so you can check also in one of the React official repos. This is in the RFC repo, also under React.js. They remodeled the context APIs using algebraic effects, and they even documented that at the time. And then when they were also drafting for, this is a third React official repo. This one is called React Basic. And it's also a dump for throwing ideas from the core team, or it used to be. And this example I took from that repo, which was introduced many years before Dan Abramov's post. However, we can see that at the time, Sebastian Mockburg also had similar ideas of experimenting with similar structures. Both the repo and the blog post, they're not talking about real JavaScript. They are wondering what life would be like if JavaScript had this kind of thing. And instead of throwing here, Sebastian thought of the word raised, and then instead of catching, it would have this special catch effect directive. And then years later, in the hooks API, if you check the RFCs that introduce the concept of React hooks and those initial hooks like use effect and use state, in the discussion thread, Sebastian also mentioned that in his reading of what an effect handler is, hooks are actually algebraic effect handlers. And when I tried to interpret what Sebastian said in that long discussion thread, I think the abstraction was more like, okay, so those algebraic effects are a set of operations and a set of handlers. And if we were to think about that in React, those operations are our hooks, like use state, use effect, and all the other 20 we got throughout the years. Not precisely 20, though. Where I think the difference here is in a language like F or Coca or other languages that implement effect handlers, we have to be the ones handling it. In React, it seems that what they try to do was to implement the same effect experience, but React internally is the one catching and handling this kind of effect and handling this as part of the render cycle of React itself. And that's basically, so the handler is React being responsible for when and how those effects run. And I think if you ask me, I would say this was probably to offload some complexity from application code into React code. Last but not least, all the way to how suspense works. So who here has ever implemented a library that is suspense compatible? All right. So basically, if you check the source of, we'll, by the way, see this today. But if you check the source of these libraries, they all have something very interesting in common. That is, you literally throw JavaScript promises. So this is the source of React Fetch Suspense, but all of them, any library that you use, like in probably React Query, SWR, or anything that is actually suspending a React component when running something async, at some portion of the code, they will have something very analogous to that. And you can even find in the original drafts of the React cache package, this is also part of the React, or used to be part of the React repo. So the way suspense works internally is that the components suspend the fiber, see? This is how it's important to have metadata about things. But a component suspends the fiber it is running in by throwing a promise, and this promise is caught and handled by React. So if you think about it again, it's the same throw, handle, resume pattern, but in a language where this pattern is just not implemented outside of the box. Before we move forward, as I mentioned, so this is the language I used in the first example. It's called F. I am yet to have contact with anyone who has ever worked with this, but it's a very interesting language. If you like learning new languages, you might also want to check it out. And there's also Coca. Coca is another language designed with effects as a first-class citizen. Not to mention that if you've done any OCaml multi-core actually tries to bring effect handlers into it. Questions? All right. Now we can finally talk about scheduling. So let's talk a little bit about browser and the tasks that run in our browser. So we've been talking about units of work. And in the browser, a task is pretty much a unit of work that it needs to perform to render a frame. So that includes handling our JavaScript, styling and layouting, all the way through the paint and composite states. So this is most of the times fine, but we may run into scenarios where we have long tasks. And the anatomy of a long task, let me turn off the profile. Actually, I'm going to keep the profile. Let me just close it. So here I have some input, and as you can see, this is totally working. This is a regular anchor. This is a regular anchor tag. This is a regular checkbox. I can also type it all the way here. It all works. If I virtually block the main execution thread of the browser, then this happens, and then things become unresponsive. So this translates into really bad user experience, as you may wonder. You've probably had contact with these when you are profiling your web applications, trying to find the culprits for slow experiences or not smooth interactions. So they are always marked with those red flags when you are profiling. And wait, this for some reason, yeah, it was still crashed. Yeah, and they so much exist to a point that I showed you a virtual example, of course, but this actually happens a lot out there, and they even result in actual human behavior. What you see on the screen is what UX people call rage clicking. So you've probably been in this scenario, you click a button, it doesn't work. Maybe it's performing some requests, maybe it's performing something that's very heavy, and then you get mad and you start clicking it all over in hopes something will happen, and a lot of times it doesn't happen. This is when we keep clicking the elevator, for example. And it exists to a point that we even came up with metrics for that. For example, first input delay, which used to be a recommendation on Web Vitals. It was then replaced by INP, but first input delay was measuring this kind of thing, for example. So it's super common that this happens because long tasks are blocking interaction. And the magic number here is of 50 milliseconds, and that's not actually a magic number. This is coming from a lot of research by the Google team mostly. There's this user-centric model called RAIL. RAIL is an acronym. So yeah, those are the ones that take more than 50 milliseconds. And the bad thing is not just that they are long tasks, but they block other tasks like we saw in that example. Now we come to the discussion. Okay, how can we then avoid blocking the main thread? And there are many different approaches for this on both React and React Native. Actually, yesterday on my way here, I was watching a talk by the team behind React Links. If you've seen React Links, is the new competitor to React Native. It was created by ByteDance, and it's basically what TikTok is built upon on. But there are different task running strategies in general. The first and most obvious one is when you have parallelism. So you have multiple threads and you have multiple tasks running in different CPU cores. Then you can have concurrency when you have a single thread, but you're quickly switching between tasks so that they sound parallel. And then you have scheduling, which is basically you have concurrency and you come up with a specific heuristic, or set of heuristics, and you attribute to a scheduler how to interleave tasks. So if we were to visualize, this is what parallelism would look like. So back to our previous 4 tasks. And concurrency and scheduling would be something along the lines of that. So let's start the other way around and let's talk about parallelism. So when we talk about parallelism in the browser, we mostly think about web workers, where you have the data happening via post message, which is basically a message passing mechanism. And overall, you have some limitations, like you don't have access to variable or code from the page that created the worker or from the worker to the DOM. And when you are writing code on top of web workers, you end up in one of these 2 buckets most of times, either following something that looks like the actual model of Elixir being a lang, or something that looks like shared memory. So if we're talking about actors, if you've seen some languages that runs in the Beam machine, basically it's an abstraction where each actor may or may not run in a separate thread, and it fully owns the data it is operating in. And all actors can do, all this abstraction of actors can do, is they can send and they can react to message. If we're thinking about web workers and parallelism in the browser, it's like our main thread is the actor that owns the document object model and the UI in general. However, you have a few drawbacks here. The first thing is that every message you send needs to be copied, because again, you're copying objects, serializing them, sending them over. And also, you need to balance, you are moving code to worker because you're processing something heavy over there and you don't want to have the main thread busy. But at the same time, you may have the communication overhead of copying what you're in serializing what you're moving to the worker, or also the fact that you may have to handle what happens when that web worker is already busy. Because overall, post message is a fire and forget mechanism. It has no underneath understanding of request and response and waiting for things. And we'll talk a little bit more about web workers, by the way, and how some of these problems I mentioned have already been solved. Before, another abstraction we can come up with is having shared memory. So this relies a lot on shared array buffer, which is one of the most amazing things that have happened to the JavaScript language in the recent years. And this API gives you a linear chunk of memory that can be manipulated using typed arrays or data views. And the interesting thing here is that if you send one of those over the wire with post message, on the other end, you're going to get a handle to the exact same memory chunk. You don't have the overhead of copying things over. However, we are talking about JavaScript, we're talking about browsers. And the world of web and browsers was not built thinking about concurrent access to objects. So most of the time, you end up having to build your own data structures to handle this kind of things, like mutexes and these other things we also learn in operating systems class. Also, you're handling a series of bytes, so you're not handling your familiar objects and arrays and stuff. Then we have WASM, which is also amazing. It's kind of like if you mixed workers with shared array buffers and you got the threading model of something like C++ or similar. And it's, I think, the best experience if you're thinking shared memory model. It's a lot of times faster than JavaScript, especially at these conferences these days. It's very, very easy to find very, very good case studies of moving something over to WASM. And I myself have a case study of a side project I built off with a friend that was basically reverse engineering a run in a separate thread with WASM. But the more you have to cross over to JavaScript to handle actual DOM, then the slower it gets. That's why a lot of the frameworks, all of the React alternatives and similar alternatives that are getting better and better mechanisms, better and better benchmarks, they still don't have scale as well for doing things like React. Because to this date, JavaScript tends to be faster at DOM rendering. And also, WASM doesn't offer a lot of the benefits and comfort of JavaScript, and I mean actual developer experience. People are more seasoned writing browser code, JavaScript code, than they are writing C++ or Rust and compiling that to WASM. I do have a disclaimer, so a lot of the problems I have raised with workers and shared memory model and parallelism in general, they are getting better and better. For example, we have the atomic specification that is something really, really interesting. Not to mention that a lot of open source projects like Conlink and Worker done by the Google Chrome team, they improve a lot the overall developer experience of working with web workers and stuff. There's also very, very creative projects like PartyTown. PartyTown is a project by Builder.io, the same company that created the Quick library and other stuff. And PartyTown is based on web workers. What it does is it allows you to offload third parties to a web worker so that your main thread is not busy processing, for example, your Google Analytics script or something like that. However, if I were to summarize in the TLDR, works are really good for data processing, and when you have to crunch numbers, I myself have a case from 7 years ago when we had a lot of mathematics running on top of layers of Mapbox, and we ended up with lots of web workers dealing with that. But they tend to be hard to use for UI-related stuff, and they tend to be harder than just adjusting it to a scheduler or a general concurrency-based model. And that's really interesting because in a lot of React conferences, I've asked a similar question on the stage. If you were to summarize concurrent React into one word or two word stops, like what would you go with? And the 4 clouds you see are from 4 different conferences in 4 different countries. And the vast majority of responses were saying that it was about parallelism, or about, some people mentioned threads over there and workers and stuff like that. And it's interesting because scheduling in React is totally about the opposite. So there's no parallelism, there's no internal understanding of threads and workers. It's all about a scheduler. And we'll talk about this, but we'll first take some steps back and make something that is very heavy. So let me open this experiment here. I have this simple text field, and what I'm doing here is, let me Jenkins input. So I got this resourceful component that's calling a resourceful operation in its render method. And what this resourceful operation is doing is it iterates up to million, and then it changes that string. So it's meant to be slow. So I don't need a lot of effort. This is a Apple Silicon Mac with no throttling whatsoever, and you can see that it's already super laggy. I am typing, you can hear me typing, but I don't see what I'm typing. And actually, if I continue for a few more seconds, my Chrome is going to crash. So it is slow, and this is not the ideal kind of experience. So we could think of many ways of improving that. There are certain patterns for more than 10 years, like throttling and debouncing. Or we can get a little bit more creative. Who here has ever used this thing called Redux Saga? All right. Oh, you have. How do you feel about it? Oh, so that's the thing. I take a lot of pride in having used Redux Saga because every time I ask this question, people always have bad memories. I also have some bad memories, but I take the fault in that. Not me, just me, but the whole team. We ended up doing a lot of very, very ugly stuff with Redux Saga. I'm not saying it. So if you've never used it, it's a middleware for Redux that was super popular. Not super popular. It was like top 3, top 4 popular middlewares for Redux about 8-10 years ago. And actually, Redux Saga was brilliant in a sense. It used generators, which, by the way, is one of the most brilliant things that happened to JavaScript in the recent years. I'm going to say the sentence 3 times. So I first said with shared array buffer, I said with generator, and I'm going to say with a third thing. But it used generators to handle a bunch of things like parallelization, concurrency, race conditions, canceling tasks, and a bunch of things. But don't worry, we will not have Redux Saga in the next example, but we'll learn some lessons from it. So let's see our second example here after. So same text input doing the same resourceful operation, but I'm going to type, and you can see that there's no lag at any time. What you can, of course, there's some UI flickering because I'm suspending my component, but it's responsive at all times because the execution is always yielded back to the browser so that the browser can handle my typing, and it renders a nice UI fallback that it's performing something that's taking all my CPU, but you can see I typed all over. So what am I doing here? Let me close all of that. Let me go back to the Jenkins input scheduler example. So I got my same kind of resource component, but now I'm calling this fast _ resourceful operation. And what I do is I create a new scheduler object, and I pass some initial value. That mathematical operation starts at 0, of course. And then I call a method called perform unit of work. By the way, the reason I'm using this is that I want to draw a parallel with what React does underneath. And the source of that function is the only difference between that one and this one is that this one is a generator. And let me go back to the slide here. So the difference is the resourceful operation we had, I turned that into a generator function. And yes, there's a very weird while true that probably brings you some bad memories from the Redux Saga time. But the reason why I'm doing this while true here inside the generator is just so that I can then use yield and yield execution back to the browser main thread. And then the rest of the code is this we already discussed. And I just want to show you something else. And this whole scheduler, it's implemented in about 50 lines or so. So it has a state and noon where basically I'm telling, let me zoom in more. So it can be idle, pending, or done. And then my scheduler class, it has a constructor that's not relevant here. And this perform unit of work is basically a switch case where I go through the 3 different states, whether it's idle, whether it's pending, or when it's done. And the 2 key things here is that I'm throwing promises. So that's the secret between the suspendability of that scheduler. So that's when we have our fallback state and we see performing unit CPU bound operation. You can see here, okay, so this is my suspense fallback performing CPU bound operation. This is a regular suspense. I'm importing that from React. There's no hidden magic in here. And then I got my resourceful component as children below that suspense fallback. So back to my scheduler. So back to my scheduler. So this is one of the tricks, and the other trick is that when things are pending, I'm going through the next method of my iterator within this generator. So, by the way, I'm not saying you should go home and implement this kind of thing. This is more of an exercise showing how we can be creative about scheduling tasks and how powerful generators are, and also how suspense works underneath if you ever need to write a library that is suspense compatible. All right, oops. So you've had spoilers already, but the result of that is very, very similar to what we would get if we had used transitions from the modern versions of React. So instead of using my underscore resourceful thing, yes, I could have just wrapped that with a store transition, and we would get something very, very similar. However, I wanted to give you this counter example because under the hood, it's not like React is doing generators and while trues. The heuristic is it's the same cooperative multitasking model. Yes, you have a single interruptible rendering thread. And yes, rendering can be interleaved with other main thread tasks because basically an update can happen in the background without blocking response to new input. So all of these boxes we've checked in our previous example. So that was all true. Response to the input was cruising good in that example with our generator and stuff. What React does is basically this. So let's say you have this original rendered task, then you got some user input. That also the same thing that happened in our example. Because it's user input, it has higher priority, so it happens right away. But then the scheduler of React, as soon as it can, it interleaves back with the original rendered task. And the magic here, let me show you. So yes, you can find this in the source under this function called perform unit of work until deadline. And basically, this function changed how it worked from one version of React to the other, because this is what it looks like with React 18 onwards. So this function that is basically the one responsible for performing work, it now uses this other function that is should you to host. And this is very interesting because they're not using generators, they're not using anything like we did. What they do is they have a magic number of 5 milliseconds. And it sounds super magic like those things we do in CSS sometimes that fixes the thing. But here it actually has a good rationale that is it's smaller than a single frame, even when we're talking about 120 FPS devices. So it doesn't block animation, and that's why it feels interruptible, just like our other scheduler. Another very, very interesting concept that lives in the same part of the code are the different priority levels. So you can find them in the source of the React scheduler. And you can see that, again, all of them have assigned a number. And you can find the same things all over the reconciler, React DOM itself, and React DevTools. You can find all of those different priorities. And basically, they will have different timeouts assigned to them. So remember how almost an hour ago we were talking how React has this data structure that models things very well, models the units of work very well. and allows it to prioritize things. So that's part of how they prioritize things. Going from what things that needs to be synced to things that can wait, all the way down to things that can wait to 10 seconds, or all the way down to things that can wait to when the browser is idle, for example. And the things that needs to be happening immediate, for example, are user input, so that the first problem we had doesn't happen. Another concept that also lives within the source of React are render lanes. So they are an abstraction built around bit masks. So one lane in React equals to 1 bit in a bit mask, and each update in React is assigned to one lane, and each render can be assigned to one or more lanes. And then, again, about React controlling and batching work together. Updates that are in the same lane, they can be rendered in the same batch, and different lanes they render in separate batches. The reason why this is powerful, and the reason why they even use bit masks, is because it gives them 31 levels of granularity, because that's how much you can fit in a bit mask. So this allows React to choose whether they can want to render multiple transitions, as in start transition, use transition, in a single batch, or render them independently. And it also reduces browser overhead, like multiple layout passes, style recalls, and paint events that would be overhead in the browser. For me, all of that is really mind-blowing, but I do understand that sometimes this can be also hard to correlate to, okay, how can I apply that in my work? I'm not building developer tools. I'm not building this kind of thing. So I've gathered a few use cases around concurrency and scheduling that I think that can be helpful. The first one is when you have to handle large sets of data, because, for example, what I showed to you, that was something that never happens in real life. We don't iterate up to 2 million in our browsers, in our components render. And a lot of the benchmarks around concurrency scheduling and every new React feature, they are around things that are very, very non-practical, like running an algorithm to find prime numbers, or running one of those algorithms that crack passwords and are super CPU bound, or even drawing the Sierpinski triangle or other fractals. And they do have to use this kind of thing in benchmarks because it's a very good way to benchmark stuff. But I do think we have very practical cases in our daily basis for this kind of thing. For example, as front-end developers, there will be scenarios where we have to render many data points, or when we have to render data on a canvas and using off-screen canvas is not available because a certain browser I need to support, or when we have to purely process just lots of data. So React themselves, they have one good open source example, just this app called Open Targets. They are a serious open source app that basically have to do they basically show clustered charts around different drugs and their chemicals and stuff like that. And they actually publish this different snapshots of running. So this is on a fast computer with no transitions, but you can see it's still fine to interact with this slider, and that the clusters still go as you would expect. But then they showed this example on a fast computer and with transitions. So the delay you see here, because then it prioritizes the input, in this case the slider, and then it performs the heavy operation. But then the good thing is on a slow computer, because you can see that here this slider is super laggy. I'm not sure if the video is reflecting that really well, but it does have some input jank. And then on the slow computer with transitions, basically it's far better because the slider is at all times responsive. And when I see this kind of thing, I myself wish I could kind of go back in time. One of my favorite performance cases I had at work, this was 8 years ago, was when I was working with maps, as I mentioned before. And I had this one app where basically I would have 100,000 data points plotted over, it was an asset curation system, and it had like 100,000 data points plotted. And at the same time, it had to allow the administration to search for them and filter them and all of that. And this was all synchronized with the React state with the map box state, and with the URL state, so that also you would have like the zooming or this kind of map state reflected in the URL too. And there was a lot of mathematical operations happening in the map too that you could run. And at the time, to optimize the performance of it and make it something good, we used a lot of web workers. So there was a lot of, like, there would be some scenarios where we had 8 workers at the same time. We used Redux Saga, partially, I would say 50-50. 50, we had a good use case for that. Other 50 was because we were already using it in other apps. But that's where my good and bad memories come from, Redux Saga. And we also used debouncing. Like when I was showing the example, you probably thought, okay, I could have used debouncing or throttling or one of those similar techniques. So at the time we used debouncing, but some of these things we could have just used transitions if we had them at the time. And another example was, this one is more recent, it was 5 years ago. So I was working for this game. It's even difficult to explain that, but this game is basically like, it's a startup idea. Basically, there's a real goal and a real goalkeeper and LED panels behind the goalkeeper, and people play the games from their smartphones. And there was this robotics guy who created a machine who would take with many complex algorithms of where people clicked, all the players in their smartphones, that would shoot the ball in one direction. This is the context. The interesting part for this here was basically there was the admin panel, because they would invite an influencer or something like this to run the live matches and entertain people while it was happening. And in this live panel, let's say we had 5,000, 6,000 people playing at the same time. And it's a football game, so people would curse a lot, for example, and say things that should not have been said. And also, there were some premium players who needed their messages to be said live on stage. So this admin panel was used by the person running the live game. And this person needed to be able to search and filter for these messages and do a lot of operations on top of these live incoming messages. And on the front end, we used a lot of virtualization, which, by the way, we'll briefly talk about today, and some memoization, but we could also have used transitions here too. But another less popular maybe example is tackling wasted renders. So it's one of our life goals as React developers, not to have unnecessary re-renders and stuff. Who here has ever heard of this hook? It's called usync external store. 2 people. Okay, yeah. All right, so it's a fairly simple hook. It doesn't take many parameters. It takes a subscribe function, and it has a method that's supposed to return a snapshot of the current state. And the third parameter is the second one, but if you're doing SSR. And this hook was initially marketed as part of bringing concurrent React for library maintainers. So this was 2021. Ricky, another core team member of React. Basically, the original idea behind this hook was to solve UI tearing problems that concurrent React caused in a bunch of state managers all the way up to Redux itself. And that's why you can also find talks about this hook and other things from the concurrent umbrella of React addressing it, and state managers mostly. Also, in the source of some state managers, this is in the source of Valtio by Poimandres, but if you check Redux itself, you'll also see that they use usync external store underneath. I think React Query does too, so anything that is concurrent React compatible and has a state manager, in a sense, probably uses that. But when we see this kind of thing, I don't know about you, but I also feel like, okay, how can this correlate anyhow to what we're doing on a daily basis as React developers? So I wanted to bring a more tangible example maybe. I'm pretty sure that if I do the raise your hands thing with React router, then all of you or most of you will raise their hands. So I have an example with use location. It's one of the most basic APIs of React router. So we can use location to get path name, hash, and a lot of other information about the current route of our app. So one detail about this thing is that this is an over-returning hook. So it gives us, most of the time, a far lot more information than we actually need to. And this doesn't mean, by the way, this is poorly designed or has any API flaws. Is not the case. But let's see something interesting. So let me open again let me open an example with use history selector. I am going to open my profiler here. It's highlighting. Let me show you what this code looks like. Jenkins bit use router selector. So I got a before component here. So you can see I'm not doing any magic. I'm not doing any magic. I'm just calling use location right out of React router done. And then I am getting path name and I'm getting hash and I'm constantly logging that. And I have my batch component that takes path name or hash. So this renders into this. Let me zoom out a bit so that the UI is not that broken. So here's my path name. It checks if you check at the top of the application, and here's my hash. And I got a bunch of components that if I click them, they will push to a new route. Let me close this. So let's pay attention to this. So if I click here, you can see that it changed my hash. So it now goes to example 1. It goes to example 2, and so on. But the interesting thing is I am not pushing a new path name. However, you can see that my path name is re-rendering all the same, even though I'm not pushing a new one. Path name re-renders. Of course, this is not a problem for an app this size. But let's go back to the slides. Yeah. We could fix that with the use history selector thing. And so here I got use history selector coming from this utils folder I created. It's let me give it here. That all I'm doing is it takes, as the name suggests, a selector, and the selector can derive information from, in this case, my history object. So I'm saying that here I want to watch location.pathname, and here I only want to watch location.hash. So let's see how it looks. So you can see that now I am clicking of course this component is changing because it's watching the hash, but you can see that the one watching path name remains unstable with no further re-renders. And this is all due to using his history selector. So under my history selector hook, I don't have many things actually. My get snapshot function is basically grabbing the current value of window.location, and my subscribe function is basically listening to window pop state and other window route events, and then I am passing, this app is not SSR'd, so I pass the very same get snapshot method as the third parameter. So yes, this is what it looks like. We already talked about it. We already fixed. And if you check the documentation, and this is the current documentation, by the way, you can see it's at the 19.2 branch. When they are talking about use history selector, they describe it as a way to subscribe to any external store. And they mention that this kind of store can be, for example, browser APIs that expose mutable value and events that subscribe to those changes. So that's precisely what we just did with the native browser routing events and state. But you can do something analogous with pretty much any APIs, like, for example, offline and online status. So we can create a subscribe functions that adds two event listeners, online and offline. We can create a get snapshot function that returns navigator.online. And then we can use history selector, using external store. We can pass the subscribe function, and again, I'm repeating the get snapshots because this is a non-SSR app. And what I have is something that re-renders when the browser is online or offline. And you can see that at no point I needed to create use states calls or use effect calls. This is very clean and following one of the use cases that they themselves describe for using external store. The last example I had for this is the creating async components. So you've probably seen this use hook and you got it right if you've not seen it. It's just use, not use state, use this, use that. No, it's just called use, and it's a way of awaiting inside components, and of course without using React server components and this kind of thing. And yeah, so if you check the official documentation, you can use to read the value of a resource like a promise or a context or something like this. But the thing is, use is actually fairly new. I mean, lots of apps out there are not running on React 18 and do not support the concurrent umbrella of things. The main app I maintain at work, for example, it doesn't. So before React had it, one thing that I use a lot was Suspend React. It's a library also by PyMonders that they basically give you a similar syntax for it. So they give you a suspendable hook that you can pass to it any sync awaitable thing. So let's see what it looks like with suspend, use transition, fibers, link input, suspend React. So this is an example of creating, let me show you it running. Suspend React. So you can see here, there's not a lot. What's happening is I have a promise that resolves using a timeout underneath after 3 seconds. So you saw the suspense fall back in there. If we check the source code of this component, so loading suspended data, and we have our hello component. And our hello component is not resorting to use to any of those library out there, so I'm calling a custom suspend thing. So think of it as it react.use, but it's not. It's my custom suspend thing. And my promise is, as I mentioned, a delay, a virtual delay. And our custom suspend thing is about 50 lines of code, but guess what? Most of this code is actually caching boilerplate. What I'm doing here is I'm caching the results of those promises and stuff, because caching is actually one of the most complex things for libraries like whatever state manager / network fetcher like 10-stack query or anything like that, or use SRR or Apollo itself or other client fetcher / state manager. A lot of logic goes to caching, but one thing I have inside here is, again, my promises that I'm throwing. So this is what makes my custom suspendable. And you might be asking, why is this relevant? Simply because, so React use is something new, and for some time in time, things like suspend React didn't exist either, and then someone created them, and then we could use it. But there will be points in time that you will need a sort of abstraction that's yet to be created, and you could be the one having or willing to create that. So yeah, it looks a lot like React use, and if you check the source of SRR by Vercel of 10-stack query or Apollo again, or any other client query manager, you will find something analogous to that. But of course, those 50 lines were oversimplified just to prove a point. And yeah, so this is a screenshot of actually this friend of mine a few years ago. He was debugging this problem, and I use this screenshot basically because he figured out because of what was going on in his suspense boundary because of one of these internal implementation details that he was aware of, because we were discussing about that before. And it's funny that actually this particular friend is the one who back in 2016, he was the one who motivated me to be into this kind of thing. Because what happened is, so we would code a lot together even though we were for separate companies, and then he it was this specific React conference where Jared Palmer was announcing Suspense. So they announced hooks, and then there was this talk of Jared Palmer announcing Suspense, and in the talking he was doing a live demo of porting all of his famous libraries at the time to be Suspense compatible. And when I watched that talk, I was super surprised, because what I was seeing there, my friend had shown me 3 months before, and I asked him, and he actually had a feature branch of his company. He had a feature flag already, and he had implemented all of that. So he had redrafted the whole data fetching layer of his company back in 2016 or 18 to be Suspense ready for when Suspense was stable for data fetching. And then when I asked him how did he know if that thing was just being announced, he told me that he was following the PRs where they were actually implementing, and he was aware that they would be working by throwing promises to be handled by React. So this, for me, is all really, really amazing. Anyways, I want to talk a little bit more about scheduling on the web before we move forward. So you're probably wondering, okay, we discussed a lot of CS concepts. We discussed a lot how React grabs inspiration from some of them into it. What does the browser have? Because the browser does have scheduling primitives. You've probably used set timeout or something fancier like ref or request auto callback, or if you've used workers, you use post message, which is also technically a scheduling mechanism. Some of these are great, but the problem is we as browser, we lack a unified scheduler with unified APIs. Because what happens, bottom line is, if you have more than one scheduler, for example, React has its scheduler, Svelte has its scheduler, Solid, and so on, not to mention that the browser has its internal scheduling things, you can end up with resource fighting. Again, I know that it doesn't happen often that you have 2 major UI libraries or frameworks running all together, but it actually can happen. And you can run into resource fighting things, or when you have state managed by something that's not React, you can also have resource fighting or condition races or anything like that. Not to mention that also we often end up in having to interleave browser work with our tests, and browser work can be rendering itself or garbage collection, all that. To address this problem, there is an ongoing initiative by the Web Consortium called the Prioritized Task Scheduling API, and it's an umbrella for many, many different APIs. So this is supposed to be this more robust solution that we've been missing for such a long time now. And again, it's supposed to work outside of the box, integrated directly into the JavaScript event loop, and it should give you a flexible but united way to control and schedule tasks. And it's the result of many, many discussions with Google, with Meta engineers, with the Web Consortium themselves, and a lot of people. If you are more interested, not just about this API, but actually how the browser schedules tasks and how V8 and Blink and all that work under the hood, there's this great talk by Shuby and Jason Miller. So Jason spent a few years working for Google after having created Preact. He's now at Shopify, but you can check this talk. Is from 2018. It's very interesting. A few things are still relevant to this date. But the umbrella of the native scheduler umbrella has APIs like post task, yield, wait, and is input pending. Some of these are drafts, some of these were taken back, some of these are still work in progress. But this is one example of the kind of power we're talking about here. So is input pending, we can do navigator.scheduling.isInputPending, and it actually should tell us if the browser is busy handling input. So remember how in our very first example with the generator-based thing, we had a while true, and the first line within that while loop was yielding back to the browser. So this is a nicer way of achieving something similar. Nice enough to, the font is small, but this is the point in the React source code. So a half an hour ago, I showed you that should you to host function and how it works, the 5 millisecond magic number and etc. They have actually implemented with experimented with is input pending underneath to use it instead of that 5 millisecond delay. But this is feature flag protected and no one is running that. But this is an example of the kind of power of having a unified umbrella in the browser native to the browser. So this is the if block that basically returns that basically uses the thing inside should you to host. And you can, again, find all of that in the source code of React. It's open source. But there are some interesting case studies by different companies. Meta, I know that they were the biggest pusher for is input pending. That, again, probably at this point in history, it even has a different, a whole different working mechanism and has been pivoted into something else. But Airbnb, they also have a case study from a few years ago using another API of that umbrella of APIs. It's called Post Task Scheduler. And there's also this repo on GitHub. It's called Main Thread Scheduling. And it's not a polyfill, but it's more like a library that has been strongly inspired by the spec of the native scheduler API. Of course, it's also important to highlight that just like anything else, that cliche of not having a silver bullet and etc. is true pretty much everywhere. So if you have code that used too often, you can also have some overhead of scheduling tasks, and it can be bad. So all of the things that we talked about here today and all of the things we'll talk in the rest of the time we have, they always will have pros and cons, and we need to think about it. So I had planned a 10 minutes break now because I feel like it may have been done so far. But how do you feel about it? Would now be a good time to go for water, to the toilet, grab some coffee, etc.? If everyone is on the same page, then we can have a 10 minutes break, and we can all be back here at 4:50. Do you want more than 10 minutes? By the way, I'm really not opinionated, so if anyone is like 15 minutes or 20 minutes, just shout that out loud. So 10 minutes now. All right, cool. Wow. All right. Yeah, let's start again, and there will be many different tiny sections, so if more people rejoin after, they will get a chance to catch up anyways. This other section is a very it's a collection of a bunch of other stuff that I think that in different years they have helped me with performance in the apps I was working with. Here I got two sections, one about React and one about more general stuff that also works on the web. So in React, and there's like an asterisk because some of these they also may work outside of React. The first one that did help me with bundle size or bundle footprint cuts back in 2018, and it did again in last year, is aliasing React to Preact. So if you've never heard of or never used Preact, it's this smaller alternative to React. It was created by the guy that I've mentioned multiple times here, Jason Miller, and this is an overall comparison between the bundle footprint of React itself and of Preact. So you can see it's kind of like 10 times smaller, and it also brings a faster VDON implementation, and they claim they have more effective memory usage. And besides a bunch of companies actually using Preact in production, mine is now using, by the way, in the app I maintain and in a few other apps we have. They are also the source of inspiration for other open source initiatives. So I don't know if you know Remix by Michael Jackson and Ryan Florence and the guys. So Remix version 3, it started as a fork of Preact, even though I don't think in the current state of the version 3 they are using Preact anymore, but they did ideate it a lot as a fork of Preact. And this is a talk by the ByteDance guys I was talking. So this talk happened 2 weeks ago in Poland. And amongst a lot of other stuff they mentioned, especially around parallelization. So if you're a React Native developer, I totally recommend you to watch that. They mentioned the sources of inspirations for the mental model of what they were trying to do with links. And Preact is also listed over there as one of their three main inspirations for what they were doing. So for this example, I also have one tiny demo. Let me go over. All right, let me pop up VS Code here. So I'm gonna open my vid config file, and you can see that I'm using the vid React plugin. So what I'm gonna do is I'm gonna just use the Preact one instead of the React. And before I do that, let me actually take a snapshot for you. So I stopped the developer build. Let me clear this. So let me run the production build just so that we have an idea of how big we're talking. So this is the current version of our app. And the main bottle, so there are a few components here that, as a spoiler, you can see that they're lazy loaded for the next demo. But the main bottle is at 300 kilobytes. So now let me do the demo I wanted to. So I'm going to comment this out. I'm going to, instead of this, here. And what this plugin is doing, and by the way, this is, of course, a vid plugin, but you can do the same thing with Webpack. At my job, we use Webpack in this app, by the way, so you can do the same thing, because at the end of the day, what you're doing is where you find reference to one module, replace that reference to another module. So that replaces references to React and React Done with Preact and Preact Compat. So Preact Compat is an official compatibility layer from Preact to make it just work with React code. So this is it, and we can run yarn build again. And you can see that it was a impressive difference. This is the only change that I made. I just replaced one for the other, and my main bundle is almost half the size. So this was the tiny demo. I also had a screenshot in case the demo went wrong. Yeah, this was with another code. And those screenshots here are actually from about a year ago when I was working with that change from React to Preact at work. So our main bundle went from 205 all the way down to 175 by just using Preact at the time. So this doesn't include any other of the performance optimizations we did. Another thing I wanted to talk about that also happened to me in different jobs and different occasions was windowing. This is the most famous animation to describe what windowing or virtualization is all about. Basically, I think I have a demo here. Yes. So let's see the. Yeah. So I have a regular list, and I am going to push this list all the way to 10,000 elements. This computer is fast, but probably if I went all the way down to performance and enabled CPU throttling, yeah, with the zoom is terrible to use. What is it again? Oh, here, CPU, and we can add some slowdown like 6 times or 20 times. I think it will still be somewhat fast, but you can see like scrolling is still, and then I just undid that. Wait a second. So let me enable again performance. The font is so small for me, but I'm gonna add a 6 times the slowdown, and I have 10,000 items. So the first problem we can see here is I have 10,000 items. So this is my done size right now. And you can see that I'm scrolling here, and I'm going to scroll all the way down, and it will get to a point that is like, I give up. Those are just 500. There's like 9.5K more. And not only this goes against a lot of best practices that are about reducing the DOM size. Like having a larger DOM size is not just a performance issue, but it actually can be an accessibility issue, because if you have a large DOM tree, you end up with a large accessibility tree, and a large accessibility tree may also mess with how your screen reader is going to be able to parse your accessibility tree. Not to mention that, again, it's really huge and it can crash your browser. And you can see that every time I have a re-render in this component, it takes a bit. Scrolling is still faster. My hunch is that they somehow optimize the scrolling, specifically Blink does under the hood. But you can see that every time I have to re-render this, it tends to crash. So this was, and then I got here a window with list, and I want to inspect the DOM of this window with list with you. So you can see here that what I have are just these 10 items, and that they are repositioned as I scroll through the list. So this is what's happening under the hood, and my DOM size is perfectly fine now, because it's gonna render the ones that are visible. So let me close here just so that you can see. So it's gonna render the ones that are visible here, and as I scroll, it's gonna, and then it does have a buffer of 2 or 3, and then at the bottom another 2 or 3, so that as I scroll, I have some stuff pre-rendered. But this is also super helpful. This particularly, and by the way, there are different libraries that you can use for that. React Virtualize was the first one created by Brian Vole, and this was the one that popularized this whole technique in the world of React. Brian Vole, also ex-core team member. And then years later, he created React Window. So he created the competition for his own library, because he basically said that he learned a lot of lessons and created this new version. And then other two that are also really good is Stack Virtual and Virtuoso. So I've used Virtualize and Window in production, and in the app I maintain right now, I use Virtuoso, because Virtuoso does resolve for you a big problem in virtualization, that is calculating dynamic heights and widths of items. This is a nightmare if you got to do this by hand. So Virtuoso does this really well. In my most recent use case for this was, as I mentioned, I work with a survey solution, and it was 2 years ago, in summer 23, we got one client. They were complaining that the surveys they were sending out would crash on Safari, and it went on Safari mobile. And when I first opened that, I had a different laptop at the time that was a Apple Intel, not Silicon, and it has far less hardware. It even crashed my desktop, so I was like, I'm not surprised that this is crashing on mobile. But funny enough is, when I started profiling, I figured out that they had 3 drop-down questions, so they were asking like subsequent drop-down questions, and each question had 15,000 items in each of them. So every time you would go, your DOM would go all the way to that size. So this was the most recent, but in the past I've addressed other stuff with windowing. And one of the common symptoms that you have done something good with windowing is when you inspect your profile and you have all these red flags on the top, and after you're done, you get a far better FPS rate and all of those green stops when you're tracing a timeline of your FPSs. Another thing that I've done multiple times over the years is code splitting. So you've probably seen something along the lines of this, when you have all the dynamic imports, and then you break down what you're importing into smaller chunks, and you just import them when necessary. The most convenient way of doing this kind of thing in React is when you combine lazy and suspense, just like back in the pattern matching demo, when I was pattern matching and dynamically loading models using that. So I also had one demo for that. So let me open here. For this, we're not going to profile performance. We want to look at the network tab. So over here, then I'm going to click the first load component. Oops, I killed the app. Let me yarn dev things again. Let me undo this. let me undo the changes we've just done. So let me yarn that things again. Let me refresh this. Let me clear. And then you can see that as I click, I got my heavy component loaded here. If I click, you can see my heavy component model. And then I can do this for all my other heavy components. So if I bring this here and close this, and go back here, so you can see my heavy components loading. And this also in the current thing I maintain was particularly useful because, as I mentioned, what we were doing before is, as someone building a survey, you can add many different kinds of questions that you may want to ask in a survey. It can be text feedback, it can be a drop-down question, it can be, for example, some video or audio feedback, like record with your opinion and stuff. And one thing we did was, before, we would load all of the possible question sizes for a survey taker, when at the end of the day they might need only 3 questions. So we started code splitting this, plus other things, like when we implemented virtualization in that one drop down, we also added React Select to have a nice experience, and that increased the model size a lot. So this was another example of something we code split. So you would only download those extra almost 50 kilobytes if there was a drop-down question in there. And we kept on doing more. It's not in the screenshot, but another thing. So this is what it looks like in the network tab. So you would see the different question types being loaded because it's loading only what you need. But another thing, before I go into the next stop, another thing that we also did, yeah, this one, yes, mostly plus some other things. So one example besides the question was certain parts that imported very large question, that were not necessarily questions, but that imported very large libraries. We also code split them. And the next example was going to be something that's not a question, so but it's not in screenshot because it was introduced a few months later, was so it's none of these. But we introduced a debugging tool that was hidden behind our VPN, so it's just for engineering and technical support to troubleshoot what was going wrong with a certain survey. So it would show a lot of metadata, and it would also allow you to debug the code, because we also allow people to write arbitrary code to run in their surveys if they want to change colors, if they want to integrate with certain JavaScript libraries or anything like that. Sorry? Oh. Yeah, people can get really creative with the custom styles they want. It's actually another topic I want to talk in a bit. Is it was very complex understanding how people are creating styles, but these styles are not the ones they're not part of our model. They are basically subsequently added, like as JavaScript and extra CSS import scripts. But what it was about this is, so we needed to be able to quickly debug this. Mostly engineering is very seasoned, use developer tools and stuff like this, but other stakeholders like technical support, not as much. So we wanted to create a nice debugging experience. And by the way, I can even show you what it looks like after in my other laptop. But the key point is we introduced syntax highlighting in the code. We introduced prettier to format. So right now, this debugger utility is at 100 kilobytes. So it's almost the size of the entire rest of the app. But because we're using code splitting, it's only loaded if you're actually within our VPN, and also if you have done all of the other necessary tricks for the tool to load. So with this way, we shipped something that is very good, but it doesn't impact at all the model footprint of our survey takers. So this is where it can be really powerful. And it's kind of a good segue to what this thing I like to call form code splitting. That is, for example, these are some APIs that I hope I'll have time to discuss with you related to monitoring performance and stuff like that. And as you can see, a lot of them are not supported across the board. So the common denominator here is Safari and Firefox are very, very opinionated on implementing this sort of APIs. But hopefully we'll get time to talk about that. However, the interesting part is, remember how I mentioned pattern matching? So you can use something similar like that with one of these APIs, like this use network status is using the network API to give me, and I'll show you what this API looks like, but to give me to tell me whether the user is running on a 5G connection, 4G, 2G, etc., and their speed. And then I'm combining that with the pattern matching thing. So what I can do is, with a case where this API is not supported, I can render my video. But let's say that the API is supported and I detect that my network information, that the network is 2G. So instead of rendering a YouTube iframe or some other heavy experience, I can then render just a thumbnail of that video and add an extra button to tell the user, hey, this is this size. Are you really sure you want to download that over your data plan? So this is a tiny example. Yeah, it's terrible, but you have access to the slides. But in this first example, network is not supported. Again, I'm running Safari, let's say, and then I don't want to make any compromises, so I render the high-resolution YouTube video, as you see. However, in this next example, it is supported, and I can detect there's a 4G connection. So again, I'm going to render the full video. However, here I detected a 3G connection. So what I'm doing is I'm rendering only the thumbnail of the video or any preview. And the way this looks is, because we're using the pattern matching thing with suspense plus lazy loading, is not only I'm not rendering things, but I'm not even downloading them. So here in the 3G case, you can see that only a component called preview was downloaded. So I'm not even downloading the logic to render a YouTube iframe, which, depending again on your app, this can be something negligible. But if you're talking about downloading an entire map box rendering layer, for example, or something that's really heavy and would take a lot to download over the wire, you might want to do that. So, and this is the example when it's connected and it downloads the bottle of the 4G alternative with the video. There's a lot of other things on the web you can do too. One of them are resource hints. And basically the idea of resource hints is because a lot in the web is about what you can predict that your users may or may not do. So resource hints are one of these things where basically you try to tell the browser how to stay one step ahead of the user and keep few things fast. And you have a bunch of them that are in the form of the rel attribute that you can add to your resources. So they are pre-connect, preload, DNS prefetch, pre-render, and all of that. We have another 45 minutes, so I won't get to discuss all of them, but one quick example is pre-connect. It allows the browser to set up early connections before you actually need them, and this includes TLS negotiations or the TCP handshake. And by doing this, you are eliminating round-trip latency. So let's say you have some HTML, CSS, there's not even React in here. And let's say that the CSS specifies that that page is going to paint things with 2 custom fonts. So when the CSS is downloaded in parser is the moment that the browser will start fetching these fonts that are probably in another domain like Google Fonts or some other CDN. And then they will be downloaded, parsed, rendered, and all of that. By using pre-connect, you can move things over here because they can be downloaded before your CSS is done parsing and even need them. And then when it needs them, they will be there and will be ready to be rendered. And much more, like with DNS prefetch, you can tell the browser about the domains it will need to look up. With prefetch, you can fetch the resources in background and like when the browser is idle and store them. And the biggest gamble you can make is this pre-render thing because it actually executes them and it paints the whole view so that it's ready for you to use. Another thing is priority hints. So there are many use cases of priority hints that you can increase or lower the priority of different things. LCP stands for large content paint. You can increase some image that is there, or you can lower above the priority of above the fold resources, and you can even pre-prioritize the scripts. That's interesting. So again, you have another attribute, so it's available to certain HTML tags like images and scripts, and you can specify fetch priority high or low. And this is a less popular part of the API because you have the same thing on a fetch request. So you have a second parameter when you're performing a fetch request, which is config. You've probably seen that, but you can then pass priority low in there. Another thing is native lazy loading. You have this mostly for images and iframes. I got to use this for iframes in my previous job. I used to work for Citrix, and we had a UI builder in there that basically people could also drag and drop different sorts of things to build a UI. And one of the things was actually an iframe, but the thing is, this iframe, sometimes you would have to scroll or even navigate so that you actually got to the part where you've seen the iframe. So by using that, you can specify loading equal to lazy, and then it will only load that iframe when needed. There's even some research by the Chrome team, as always, with some interesting results of using that. They mentioned lazy loading iframes can lead to 2 to 3% median data savings, 1 to 2% FCP reductions, and 2% FID improvements at the 95th percentile. This one I also gathered under the web section because this one is not just about React. It's not even about JavaScript, to be honest. It's who here has ever heard of data-oriented design? All right. So this is I really like the Wikipedia page for it because it starts as not to be confused with data-driven programming. So a lot of people have heard of data-driven programming. Data-oriented design is this collection of techniques that it's all about analyzing access patterns and of different kinds of data in your app and picking the right data structures to optimize for the hardware where your software is running into. So those optimizations are mostly like optimizing use of CPU cache or limiting what you store and what you access from the RAM memory, and even using SMID instructions. And a lot of the motivation of this is because CPUs are fast. Like basic mathematics in CPUs, they run in very few cycles, and even the things we learn back in school that are complex math, they do require a few more cycles, like square root and all those operations that we're told not to use, but it's still okay. Not to mention that nowadays, or for some time now, we have SMID to improve throughput, and we can process multiple values in the time it takes to process one single instruction. However, what's not as fast is memory, because our CPUs, they can only operate in the data that's physically collocated. So that means the registers of the CPU or the closest cache, that is L1. Everything else you need to load, and you're probably thinking loading things from memory should be fast because it's the memory, it's not the hard drive. So if we come up with a few ballpark numbers and approximation, if we gotta get things from RAM, we're talking something about 100 nanoseconds, and I know it's nano, so if we gotta go from L2 cache, so I didn't add L3 here, but if we gotta go through L2, we're talking about 4 nanoseconds, and if we're talking about L1, it's less than 1 nanosecond. It's easier to see that if we think in terms of multipliers. We have something that takes X times, then we have something that takes 8 times X, and we have something that takes all the way up to 200 times X. How is this relevant? So to optimize for this, people a lot smarter than I am came up with many different things. One of them is called cache prefetching, which is basically where when the CPU understands that you're going to need things from that location, it go ahead and it prefetches it, and it does for the future, like for upcoming information, but for previous information too. But this and other optimizations, they work when the CPU can predict the access pattern of your data. And that's usually when you have a very, very simple or even linear access pattern. Let's talk about JavaScript again. When we're talking about data-oriented design, one of the terms that we hear most are arrays of structures and structures of arrays. This is very, very common lingo in the game development industry mostly, which, by the way, as I mentioned 3 hours ago, we can always learn about a lot from them. So this is, yeah, I realize, but it's only a few of you, so you can probably sit at the front, and you have the slides. So this is, I'm modeling here a very, very simple character entity where I got a position, which is a pair of coordinates x and y. I got a velocity that I want to apply to position another pair of coordinates x and y. And I got some hit points because imagine it's a game. So a character in a game can take damage and lose some hit points. And it's a game, so I want to spawn multiple characters in my world. So I have an array of all of that, depending on how many there should be in this world. So this is a very oversimplified example of implementing this with array of structures, which is probably, if we're doing an exercise and I ask you to implement this, or someone asked me, this is the first way I would do it, because it's very intuitive. If we were to go from that to a structure of arrays, we would have 3 arrays where we got positions, velocities, and hit points. And you can see that I'm not just using regular arrays. I'm using typed arrays, one of the most amazing things that happened in this language in the recent years. So we got 2 float32 arrays for positions and velocities, and an int16 array for hit points. And then I have this I, which is basically an identifier to tell me how to find a specific entity within those 3 arrays so that I can grab information from it. By the way, the reason why I'm using those typed arrays is because they guarantee that under the hood I'll have continuous access, continuous memory locations, plus those are SMID optimizable. Basically, the shift we're doing here is, as I mentioned, the first one, it was very easy to read, write, and model because it just makes sense in our head. We tend to bottle together properties of one entity. What happens, though, is that this brings in poor data locality, and we'll see how. But it partially has to do with accessing information from further away memories can be bad. Also, we'll see how iterating over millions of this can actually escalate not ideal, and how this can be actually harder to parallelize. And on the second example, we had quite the opposite. So we had great data locality. It tends to be cache friendly and even SMID optimizable and parallelizable, but it's far lot less intuitive. I saw some faces when I showed the second code. I was like, why are you doing those 3 separate arrays? It makes 0 sense. So it's less intuitive, and yes, depending on how seasoned we are with this mental model, it can be even harder to debug. But let's see why. Yeah. I actually had one slide talking in this section talking about object-oriented programming and how it taught us to think on the way on the right, on the left. Yes, but I had to delete it because I was afraid I wouldn't have time, because then it would spark a lot bigger discussion. But yeah, it's totally this. Yeah, there are even some talks discussing going from some OO practices to the data-oriented DoD practices. And so we started by talking about memory. Then I showed you a nice to read code, and I showed you a weird code that didn't used to be weird. And how do they intersect, and why is this even a discussion for a React/web performance thing? So we talked about these 3 properties. So position coordinates, velocity coordinates, and hit points. Let's say we want to lay those in the memory. So here in the first row, I got my first three characters. So I got X and Y, and then I got my velocities and my hit points, and then I got the next 5 being my second character and my third, and so on to the next rows all over. Let's say that I want to implement that take damage function. This take damage function is only concerned about my hit points. So it's only concerned about taking, it's going to take a value. If I were to write code, it would take a value, and then it would update, it would decrease this amount of hit points from that specific character, and it only reads and it only modifies hit points. It's not concerned whatsoever to the position of the character or to the velocity of the character or anything like that. Do you see how sparse this access pattern got? So again, I ignore the first 4 things. I care about hit points. I ignore another 4. I care about hit points. I ignore another 4, and so on. And again, this was totally a non-realistic scenario, because in any game or in anything that you would abstract like this, you know you would have a lot more properties, a lot more attributes than just 3 attributes with 2 dictionaries and 1 number. This is exactly the kind of memory access pattern that we want to avoid. So if we were to go from that thing to structures of arrays, we would have those 3 arrays where we have x and y, and x and y. And anything that is concerned about position will only have to care about that first array. The same thing for velocities, and the same thing for hit points. And that's why I meant that it can be even easier to parallelize, because you have more isolated, you can literally be touching different parts of the memory in different threads. So this is a very, very quick rundown of what DoD is mostly about. It's about thinking on small loops that will operate on those arrays of fields. And the idea is that you can minimize the amount of data in cache that isn't read or written during a certain update. In our case, the update was the take damage function, but it could be a render function that takes x and y and plots it somewhere, or it could be a move function that takes a position and a velocity and then it ignores hit points. And overall, you had several transforms that can run in parallel, because same logical objects, because they don't share fields. I created a very, very quick benchmark using TinyBench. It would take some time to go through the code, but what I'm doing here is, so let's start with the base case. I have the same code, but one implemented with array structures and one with structures of arrays. And I start with very few properties. So only hit points. In this benchmark, I'm talking 3D games. So there's X, Y, and Z, X, Y, and Z. And I run an operation. And the key column here is the last one. We're looking at the average throughput or operations per second. So you can see that the structure of arrays is far faster, but it's still something like 4 or 5 times faster, and one could say, I don't have to refactor my entire code base to micro-optimize to this point. Maybe this is a negligible gain, and I will never get to the scale of needing to worry about that, which is fine. But then we can multiply the number of properties by 5. So now we have 20 properties that we're reading and modifying in both ways. So the structure of arrays continues at a solid 975 operations per second, so a drop of only about 10. But the other one went all the way down to 10 operations per second, so that's far slower. And then let's multiply again by 5. So now we have 100 attributes on each, which again may not be your case. So one continues at 972, and the other one dropped all the way down to 2 operations per second. Does it mean that you should go and refactor your React applications for that? Not really. But the reason why I wanted to show this particular example is because for me it's very important that we think about things and strategies, patterns, tools that they thrive at larger scales. And this is a totally non-related example of the same idea. So Ryan Carniato, the author of Solid.js and Xmarco member, in 21, he was benchmarking specifically the bundle footprint produced by the different framework competitors. And you can see that it started, so the columns you see are the number of components in the app. So he started with an app that had only one component and went all the way down to 80 components. And when you had only one component, Svelte was the one producing the smallest bundle. As he added more components, Marco and Solid were doing better. And when it got to 80 components, Preact got to produce the smallest bundle. So in this, does it, again, mean that you need to start using Preact? No. But it's another example of, in this very, very specific criteria, this very, very particular tools. This was, again, in 2021. Things might be different now, but it's an example of looking at things that they thrive when at scale. By the way, if you're interested about this, there you go, OOP. I had more slides about OOP, but I had to take them out. But I wanted to give this talk because the guy talks a lot about this. So this is Stoyan. He's a very, very brilliant guy. I think he's still at Google, but this is a talk from a few years ago where he's going about how they optimized FPS and other metrics of the engine behind Chrome. And a lot of the things were about refactoring OOP code into DoD code. And again, does it mean that OOP is by definition a bad thing and DoD is the answer to your other problems? Not really, but it's, again, I mentioned that one of my mottos here was to try to open your eyes to certain patterns and how they could be applied in very, very different cases. And this thing is actually in a lot of places where we don't see. DoD and entity component systems and other metric and other patterns that are very, very common in the game industry, they are implemented in proprietary engines like Unreal and Unity. Those are two of the most popular out there. Even if you're not a game developer, you might have heard of them. There's this open source engine too. It's called ENTT for entity. This is what Minecraft uses, and I'm pretty sure you all know Minecraft. It seems that also one Call of Duty and one Diablo is also built on top of NTT. And not to mention a bunch of case studies you can see out there of optimizing things with DoD, ECS, and similar, optimizing mostly games with those things. And it's also in the apps we've built. So there's Miniplex, which is, Miniplex has a few thousand stars as far as I remember. And it's ECS pattern for building games. It's an ECS implementation for building games on the web. And more recently, there's CUDA. So remember how I talked a lot about the Poimanders initiatives, how they have Valtio, Jotai, Zustand, and a bunch of brilliant solutions for state management. One of their most recent initiatives is CUDA, which is a React first. It's an ECS manager with a React adapter, and it's based on ECS ideas, and it's also by Poimanders. Let me see. Do you have any questions, or we can move? So I am pretty sure, so we have another 24 minutes, and I still had a full session on measuring and talking the feature and some closing notes. So let me, so this is what I had in time for measuring for today. I was going to talk about 6 different timing APIs, and then about some profiling APIs, sensors, and custom metrics. So I'm going to shuffle the order of things a bit, and I will focus on profiling and on custom metrics because I really think those are super interesting, and then we can move to the next topics. Anyways, you're going to have all the slides, and so you can check that at home if you want to. About profiling, I had 3 items. So the first and probably most popular one is long tasks. So this is an API that will report, as we discussed hours ago, long tasks or things that take more than 50 milliseconds. And this one is very useful to know when the main thread is blocked. And under the hood, this is what's used to calculate the TTI and the TBT of a page. The way you would watch for this is by calling observer.observe, and you pass the type equals to long task. And the amount of data it can give you is super interesting because you may or may not have an RUM solution in place. So if you have this or real user monitoring, if you have this is already probably used to calculate a lot of metrics, but if you don't, you can implement some and send over using Grafana or something similar like Grafana with Faro RUM. This one is less popular. It's called JS Self-Profiling API. So it's not part of the performance observer. It's got this profiler constructor that takes some config, like the interval for taking snapshots and the buffer size of it. And the way you do is it gives you a trace after you call profiler.stop, and you can, again, send that to your RUM solution or something like that. And this is very interesting because you can then profile specific complex operations or third-party scripts, or even combine that with other metrics that are out there for especially the long task one or some specific timings like the event timing. And there was one that's probably even less popular. It's called user agent specific memory. So this one, the reason why I really like this one is because we tend to take memory for granted in the browser, and we tend not to be very mindful of memory leaks. And this API helps us spotting memory leaks. We'll see how. Basically, it waits for the next garbage collection, and it measures the memory immediately after the unneeded one was released. And it will also force garbage collection if it doesn't happen for 20 seconds. And it's very, very interesting because memory leaks are where we less expect them to be. For example, if you forget to unregister an event listener, or when you're capturing information from an iframe, or when you leave a web worker open, or when you have sparse arrays. So we were just talking about sparse memory. So when you actually accumulate objects in arrays and you have sparse arrays, you can have them. There's this talk on the BlinkOn 9 conference back in 2018 that is discussing how browsers, most specifically Chromium, handles memory underneath. It is super, super interesting. It is a lot about Chromium and V8. But this is how tricky this kind of thing can be. So looking at this code, we create an object. We have a property with 1001 empty array with 1000 allocation, and another one with 2000. So I'm constantly logging things here, but only A. Would you say that we have a problem here, besides me creating a useless, two useless arrays? Or let me rephrase, is B going to be garbage collected or not? No? Yeah, because it's accessible. So even though you're not doing object.b, you can in runtime do object.b, and it's still accessible. So the way this, but this was just one random example, but again, it's really easy to mess with memory in the browser. And so this API works when you do performance.measure user agent specific memory. I'm going to skip questions. I had a whole session about sensors, like battery, and gathering battery information. Like you can do navigator.getBattery, or you have some event listeners to figure out battery changes, like to understand if your user's phone is about to run out of battery. Let's say you have an editor, an iPad, and it's about to run out of battery, so you want to save some work in progress. You can get really creative. But in my opinion, the one you can get mostly creative is with network information. You can do navigator.getConnection, or you can register an event listener, and it gives you a lot of information, like whether the connection type, as we saw in the previous example, also the round trip time, and even if they got the mode to save data or not. And then you can use that like this. So serving different experiences like the video, thumbnail in high resolution and thumbnail in low resolution. There's actually some posts addressing this. This is what I really love this name. It's called Connection Aware Components. I think it's a really good way to describe what this is doing. And there's even a Google library from a few years ago that wraps, it's called React Adaptive Loading Hooks and Utilities. It's a long name. But basically, it gives you React abstractions like hooks on top of those APIs so that you can listen to this kind of information. And this is the kind of thing you can do. For example, this is a copy of the Twitter feed where you can, for example, if the user has the save data mode enabled, it will only show the thumbnail low resolution preview. And if you want to see the image, you can click and it will download the image. So this is another example. And then I really wanted to talk about custom metrics and how creative we can get with this kind of thing. For example, you can check the word of speed matters, and some people like Tammy Evers. They're always creating very, very interesting new metrics that translate some certain business impact. For example, this one is called Less Painted Hero. But what I really wanted to talk about here is user frustration and monitoring third parties. So I'll start with monitoring third parties. Okay, this is my favorite thing that happened in the last years of JavaScript. So proxies are super, super powerful and, in my opinion, very, very underestimated. There's this talk by Michel Vestrat. He is the creator of MobX and of Immer. And this talk is called Immer, Immutability, and the Wonderful World of Proxies. I really recommend you check that out. It's very, very interesting, and he's basically talking how Immer uses proxies underneath. However, one recent case study I had about proxies was, so remember how I mentioned we allow people to write arbitrary code in our app to customize the look and feel of the surveys and integrate with things and whatnot. About a decade ago, it was made the decision that jQuery would be served out of the box for people who wanted to write those customizations using jQuery. So you could shuffle elements over with just calling jQuery calls. You wouldn't have to worry about importing jQuery yourself. It would just work. And yeah, I'm going to show the demo. Needless to say that this was a problem, and eventually we needed to get rid of jQuery, to decommission it, not just because of the performance cost, but also because depending on which version of jQuery you're running, you might also have some open CVEs, and people may file vuln tickets for you, and etc. So I have an entire talk about static analysis and how we actually used AST walkers to understand how people are using jQuery. But on the other end, another thing we did with proxies in runtime was observing how often jQuery was actually executed for each survey. So here's one quick example. Let me close this. Measuring jQuery. All right. Measuring jQuery. So I have a few examples of using jQuery. Let's say for one animation, this is not React, this is jQuery inside React, or even performing a AJAX request. So I send a request to an API with jQuery. Do you see this log? So it tells me that jQuery was called, which jQuery function was called, and with which parameters. So here, for example, pen2 was called, and these were the arguments. So this is one example of creating one metric that was very, very specific to our business case at the time, that is understanding who's still using jQuery and who's not, so that we can decommission for the ones that are not. I think I will not have the time to talk about user frustration, but I had one tiny example of user frustration. That was basically this one, rage clicking. So again, a lot of other tools will do this out of the box for you, like tools that are known as DXA or digital experience analysis. But I showed you rage clicking multiple times because of the main thread was blocked and yada yada, long tasks. So here's one example of how we can actually detect rage clicks. So I'm here mad at this div, I click it multiple times, and then this is reported, and the amount of clicks was reported. And implementing this manually is actually quite straightforward. Like if I go here, in the jQuery example, this is all code to run jQuery inside React. The key part here was this use jQuery hook that would basically have an effect to understand when jQuery was loaded, and then this part that would use the proxy API and the reflections API to patch jQuery and run a callback every time the function was executed. This is a bit bigger piece of code. And then the one for, let me go all the way here, the one for rage clicks, I am basically calling this track rage clicks function that I created under this DXA thing. I pass a ref, and then I pass some config. So configuring this kind of thing, you want to think of a threshold. For example, how many clicks define a rage click, and which time window, because you don't want to think like 2 minutes, it's too much. So which time window, and also which pixel range, like a radius from a given region. So you can also check the implementation of the track rage clicks function. We now have 10 minutes, so I wanted to talk about a little bit of the future of performance, of React, of the web, and also some closing notes. So in React, there's a lot more happening. We talked about some of the internals and some concurrency niceties and all of that, but a bunch of things that otherwise in the past we would need third-party APIs like optimistic state updates or resource preloading and etc. They are now in canaries or other versions of React, or implemented at meta framework level with something like Next.js. Just 6 days ago, React 19.2 was released. I thought they were going to hold it to the React Conf, until React Conf, but no, they dropped the bomb, and probably they'll have a lot more announcements in there. But there is activity and cache utilities and the use effect event. One of them that I really want to talk about is activity. That was known for a lot of time as off-screen. It was 2 years ago, more or less, renamed to activity. And this allows you to render in the background with no additional overhead. And basically the way it works is it doesn't mount until the component becomes visible and effects are not fired. So basically this is a very, very convenient way of toggling visibility without losing the state. And there are just so many use cases one can think of it. Like routers, they can pre-render entire screens in the background so that when you navigate to them, they're instantly available. Or a virtualized list, like we talked about virtualization. So a virtualized list can pre-render additional rows above and below to the visible window. And if you check in the source, this has been in the source for quite a while now, mostly under the name of off-screen. So you can see, especially in under the reconciler, this part called fiber begin work. And one thing specifically about off-screen is, like a little bit less than 1.5 years ago, I was talking about I had a talk about React turning 10 and all of that. And one of the things I was talking about was activity, and how I saw this as a future that was almost present. And at the time, I even had this screenshot of how activity was still under research, and they were trying to finalize necessary primitives because it was exposed. You can see on the top, this was React 18.3.1, and now activity is canary as of last week. So things are moving, and there's much more, like suspense for CPU boundary. So this is a PR by Andrew Clark filed back in 2020, so 5 years ago. And even then, he created some examples where he would have this suspense component with this extra pop called expect load time. And the idea for CPU for suspense, for CPU bound trees is that you can force a fallback in the initial render, regardless of it being suspended. So basically, let's say you did some profiling and you figure out that a specific subtree of your components hierarchy is expensive, so you can render the placeholder while you run something that's CPU bound, because suspense was initially meant for network bound stuff. If you're a React Native developer, I was gonna raise your hands, no need for that. But there's something very brilliant called static Herms, that is the next iteration of the Herms virtual machine, and not virtual machine, of the Herms runtime. And the idea is that it modifies JavaScript semantics to allow efficient sound typing. The whole concept of type soundness in compiler design would be another 1-hour talk. But the idea is to bridge the C performance and the JavaScript usability on top of ahead of time compilation. And you can mix and match bytecode and native code based on your needs. There's this talk by one of the main guys working on this at Meta. His name is Tsvetan Mikov. It's super interesting. I recommend you check it out. And the benchmarks on this topic are super, super promising. Not to mention React Strict On, which is also by Nicholas Gallagher, the creator of React Native Web. He is now working for Meta for quite some time now, and he's drafting this whole entire opposite approach to React Native Web that brings a lot less overhead of rendering React Native stuff in the browsers. There's an ongoing RFC with a lot of information and architecture diagrams I totally recommend you to check out. On the web, I think we'll have more and more discussions around routing and MPAs and SPAs, and whether SPAs were even a good idea to begin with. We'll talk more and more and think of more strategies to address problems like waterfalls. Solid Start, the meta framework for Solid.js, actually has this concept of single flag mutations that is very, very powerful and interesting. We'll also see more and more things like hybrid routing. There's this talk about Astro earlier today. We'll see more and more approaches to hydration. We've had partial hydration, selective hydration. We've had resumability and whatnot, and then no hydration at all with quick and resumability. We'll also continue to explore where to draw the line, whether it's a good idea to have 0 kilobytes JavaScript or not. And I think we'll talk more and more about code extraction and other things empowered by static analysis. Dan said a few years ago, the next wave of techniques won't be about putting everything on the client or doing everything on the server. It will let you move code between them without friction and adjust trade-off to the use case. Take advantage of both, the middle way. And when I read this kind of thing, I think about things like import attributes. Import attributes is one proposal that it's been even implemented in TypeScript, and you can basically import something with type JSON. For example, I wonder if in the future we wouldn't be able to do something like this. So import a component with type client or with type both. I wouldn't be surprised. Not to mention that I think we'll see more and more infrastructure, the intersection of infrastructure and ops with front end, with edge-first frameworks or framework-defined infra and all of that. And more than ever, we'll see a bunch of people writing down pieces explaining why certain technology is the future. Finally, closing notes. For the few of you who survived throughout the last few hours, I really want you to have as takeaway that there will be scenarios where understanding internals and the motivations, the rationales behind them can help you write your own abstraction. So what I wanted to show with that was the generator-based scheduler we built with suspense generators and stuff, how we build first-class support for promises, There's two examples, JS Code Shift and Babel, I didn't get to explore. They were static analysis and would take 1 hour to talk about them. And also custom metrics. So sometimes we can come up with creative abstractions to address very specific problems. At the same time, you need to be aware, especially of all the cool things we learned about the source of React and its internals. Use them with caution. There's this variable that's super famous, secret internals do not use or you'll be fired. And there's this there's this issue on GitHub, and then had to say, no, it's not safe to use. But it turns out that a lot of projects actually use it, like Relay uses it underneath, and Headless UI. Those are two very big projects, and that's why they even had to write in the migration notes for React 19 that if you're using one of these libraries, you may run into problems. Another thing is that software in general, not only React and JavaScript stuff, is always going through cycles. Two examples. So we talked a lot about games, so I wanted to show this one. This is Andrew Clark in 2018 saying how a lot of the React mental model of having the work in progress tree and the current tree and the basis of reconciliation is inspired by this technique called double buffering. And this is something that game developers have been doing for ages now. Another example is Dan Abramov. A few years later, he said, all of these cool things that we start doing in 2020, not just React, but a bunch of other frameworks, Marco by eBay has been doing since 2014. And he even shows this post called Progressive HTML Rendering with Marco. This was in 2014. And the funny thing is that that post links to another post from 2005 by Jeff Atwood, one of the founders of Stack Overflow. And he's talking about the same topic, but with the .NET community. Another thing that is really important to me is that to see that React is always trying to address the lack of JavaScript and web platform features with their own creative ideas. Like the first time I saw this throwing promises thing, I was also like, okay, this is hacky. I didn't expect them to be doing this kind of thing. But do they have effect handlers? Do they have a lot of the other things we discussed? They don't. So they find creative ways of implementing similar abstractions. Also, please, whenever possible, all of these performance stuff, try to connect them with business metrics and with your users' metrics, because that's what matters at the end of the day. I love this post by Salma. It's about modifying your Lighthouse scores. So she grabs this app with very poor scores. She doesn't optimize nothing, just makes a way of tricking Lighthouse into thinking that those metrics are better, and then she got 100, 100, 100. So it's important that we don't game metrics just to show nice Lighthouse scores. We need to be always shipping actual improvements to your users, and this will reflect into business metrics. At the end of the day, the cliche is true, there is no silver bullet. I showed you a bunch of different things that I've used in many different occasions throughout the years, because again, for each scenario, you have to identify the core metrics and the core solutions to address your core problems of that one thing. Also, don't take networks, CPUs, and memory for granted. There are some very popular case studies. This one by Netflix is a very famous one. Back in 2017, they were running, it was about running React in displays or hardware in general with a lot of constraints like smart TVs. Flipboard also has a very interesting case study on that. And I myself have been in scenarios where I also needed to run React and JavaScript with hardware constraints. Like the game I told you 1 hour ago, or even running in the browsers that run in billboards, which guess what, are super, super limited in hardware and in their own implementations of browsers. All things considered, also try to test on real phones and networks, because this will be the best way to force you to be mindful of all of those aspects. And finally, that's all I had for today. We had to run through things a little bit more at the end, but I'm going to be around after the conference for beers, so do reach out if you want to talk more about a specific topic. I have a bunch of presentations about performance optimization, internals of things, compilers, and this kind of stuff. I really love it. And that's pretty much it. Muito obrigado.